Howdy. Here, we'll learn about the supersonic rocket nozzles and how to work out fundamental problems involving them. But first, it may be essential to discuss what the nozzle and its twin sister, the diffuser, even are. Here, we have a subsonic nozzle. It is wide at the inlet and it narrows at the exit. Think about a water jet on a hose. We will begin with making sure laws of physics are not broken by ensuring that mass is conserved. The fluid, whether it be liquid or gas, going into the inlet, has a density and a normal velocity. It is important to note we will be assuming the flow is only in the x direction. We can write the conservation of mass equation and integrate it over the areas of each side, providing us with the equation for mass flow rate balance. So the mass per second entering is the same as the mass per second exiting. As we know from putting your thumb over a water hose, if the area is decreased, the water goes faster. In the equation, the left side would be the initial water hose area, and the right side would be the area not covered by your thumb. Now, for the opposite situation. Now this is a subsonic diffuser. It is very similar to the nozzle, only difference is that it's going small to large in terms of area. Running through the same math, we arrive at the same equation. Only this time, we learn that as the area increases, the velocity decreases. Now, we can go ahead and combine the nozzle and the diffuser together. If you notice, the mass flow rate of state 1 equals the mass flow rate of state 2, while also state 3 equals state 2. This means we can say the mass flow rate of the inlet equals the mass flow rate of the exit on this nozzle diffuser combination. This is also structurally the same as a rocket convergent divergent nozzle, but it is not since we are still in the subsonic flow regime. Now, what is interesting is this mass balance holds true no matter how we want to set up the inlet and exit areas. The velocity will change to account for these changes. With mass taken care of, we can move on to energy, another important property to conserve. Thankfully, like everything else in math and physics, mass flow rate has a symbol, and that is m dot, which we will begin to use for simplicity's sake. We will start with the energy in equals the energy out, and the dot, just like for mass, is telling us it is energy over dt, or just energy per time. We write the steady state form for energy conservation for a control volume, which is the mass flow rate in times the summation of the enthalpy, the velocity squared divided by 2, and gravity times height. This is subtracted by the exit conditions, then add the heat change, and subtract the work performed by the system. Thankfully, we can assume a lot of this away, such as no change in elevation eliminates the GZ terms. This is an ideal situation, which will result in no heat transfer, and the system provides no work or gains no work, resulting in this equation for a nozzle or diffuser. Let's now run through an example to test these new ideas. Here, we take a nozzle with inlet conditions having a pressure of 40 bar, temperature 400 Celsius, normal velocity of 5 meters per second, and an area of 1 meter squared. We measure the outlet pressure and temperature being 30 bar and 360 Celsius respectively. The first thing we can do is fill in some blanks by cross-referencing the pressure and temperature on a standard thermodynamic properties table. Or you can use an online properties calculator. I'll link one in the description. That's pretty good. Now, with these values, we can solve for the exit velocity. We start with our handy energy equation for a nozzle and solve for U2. This results in 13.22 meters per second, meaning the velocity is increasing. As for the area of this exit, we can set up the conservation of mass equation and solve for A2. We find the area was decreased from 1 meter squared to 0.475 meters squared. Moving to the right, we now need to solve the diffuser. Bring in the results of the nozzle exit into the inlet of the diffuser and knowing the exit pressure and temperature conditions, we can perform the same math as before and find the speed has decreased while the area has increased. Combining the two together, we see that the overall velocity has decreased from 5 meters per second to 3.49 meters per second. And it may be good practice to redo this problem, but now, assume this was just a large diffuser, going from 1 meter squared to 1.373 meters squared. Turns out, it's the same. But now, we'll move on to the rocket converging-diverging nozzle, where this nozzle-diffuser combination acts solely as a nozzle. Now, we'll need to do a bit of math to get an equation to help us understand how the converging-diverging part and the throat of the nozzle work. We begin, as before, with the conservation of mass equation. We then take the natural log of this equation and, using log rules, separate it back apart. We then differentiate, eliminating the constant in the process. Last time, we went to the energy equation, but here we will look toward the force equation to help. Here, whole reliable F equals ma can be teased apart, creating F equals the pressure acting on the x direction of the differential volume. Next, m equals the density times its differential volume. And another way of referring to acceleration is velocity divided by time, thus du by dt. We then multiply this by dx, and now realizing dx by dt is velocity, we get du by dt times u. Put this all together and rearrange, we have this equation which is referred to as the Euler equation. We can now plug this into our mass equation, and more rearranging and other substitutions such as isentropic relations and Mach number, we get dA over A equals m squared minus 1 times du over u. This equation holds the key to how a rocket nozzle operates. We can see that if the Mach number is less than 1, meaning subsonic, the only way the change in velocity can be positive is if the change in area is negative, and vice versa for when the flow is supersonic. For the velocity to increase, the area needs to increase. But if Mach number goes from below 1 to above 1, where is Mach number equal 1 located? Intuitively, we can see it must be in the throat, and if we plug in m equals 1 into the equation, we see the change in area is 0, which happens to be in the throat also. Thus, if a flow is capable of reaching supersonic speeds, the point at which the flow reaches sonic is in the throat. But if the flow is unable to reach Mach 1, the setup acts as a nozzle-diffuser combo as seen before. This is what makes the converging-diverging nozzle different from the nozzle-diffuser combo. We have one last set of equations to go over before solving a rocket problem. These are the isentropic relation equations. We can use these because we have been assuming isentropic flow this whole time. The flow has been adiabatic, no heat in or out. Now, for a rocket engine, there is obviously a large amount of heat being generated, but this heat is being generated before the converging-diverging nozzle, so as far as the nozzle cares, it is adiabatic. And we have been assuming the process is reversible, although in real life this is impossible due to friction and such, but one can help mitigate it. We also have this monster area ratio equation, which explaining its derivation would take another video to do so, so we will take it as true for now. We can now test our converging-diverging nozzle and see how it performs and what conditions we need to make it a supersonic nozzle. Just as a recap, we have a throat area of 0.475 meters squared, and the speed of the throat is Mach 1. The exit has an area of 1.373 meters squared, and at sea level conditions, meaning pressure is 1.01 bar and temperature is 288.15 Kelvin. Gamma is the ratio of specific heats, and for oxygen, hydrocarbon, fuel gases, it's approximately 1.2. Starting with the area ratio, we can solve for the velocity at the exit in terms of its Mach number. This equation can be solved numerically, and there will probably be false solutions below Mach 1, just as a heads up. Now we need to know how much pressure and at what temperature we need to place the combustion gases under to achieve this speed. Here, we just solve for P0 and T0. So the final results are, we were able to get an exit velocity of Mach 2.367 with inlet conditions of 14.57 bar pressure and a temperature of 449.59 Kelvin, which goes to show the extremes needed to get supersonic flow. Thank you for watching, and there's always more to learn. This was just the basics of how a rocket nozzle works, but there are other modifications such as making the diverging part more bell-shaped to improve performance, so don't stop here if these topics interest you. Also, if you enjoyed the video, consider subscribing. I'll continue to make videos relating to math, engineering, and aerodynamics.